Hello students, this is Mr. Allen. Today we are going to move on in chapter 4 and we are going to look at section 4.5, which is on isosceles and equilateral triangles. Our objective today is to use and apply properties of isosceles and equilateral triangles. So first let's look at the definition of an isosceles triangle. Here's a picture of one. And an isosceles triangle is just a triangle that has at least two congruent sides. Now, in most cases, when we're dealing with these isosceles triangles, it will literally just have exactly two congruent sides like we have in this case here. We can clearly see that segment AB and segment BC are the congruent sides, and we call those two sides legs. So segment AB, the congruent sides, and segment BC, those are the legs. The base is the non-congruent side. Now, it could be that this guy is congruent to the other ones, but typically that's not the case. So segment AC is what we call the base. So the sides have special names. There's legs of an isosceles triangle, and then there's the base. The angles also have a special name. And if you look at one of the legs and the angle formed by joining the base, that'd be this angle right here. That is considered a base angle, and of course the other base angle is this one right here. So it's formed by the base and a leg. Now where the two legs come together, this right here, this angle, angle B, is called the vertex angle of the isosceles triangle. Okay, so just a little bit of terminology there. All right, this is probably the most important theorem of the day, and it's called the isosceles triangle theorem, or what we call ITT. And here's what it says. Remember, we're doing that whole P then Q thing. If two sides of a triangle are congruent, then the angles opposite those sides are congruent. So if this side is congruent to this side, then this base angle is congruent to this base angle. Let's see an example of that. So here it says find the value of X and the measure of angle C. Well, let's see here. The first thing that we notice is that this is an isosceles triangle. And the reason that we know that this is an isosceles triangle is because we have two sides that are congruent. So that meets our definition of an isosceles triangle. And by ITT, we then know that these opposite angles, the angles opposite the congruent sides, have to be congruent. In other words, angle B has to be congruent to angle C, and that's by ITT. And therefore, we know that the measure of angle B has to equal the measure of angle C. And then we can then substitute 3x minus 10 equals 2x plus 8. So that's going to give us, if I minus 2x on both sides, screw that up. If I minus 2x on both sides, I'll get x. If I plus 10 to the other side, I get 16. So I've already got x is equal to 16. Now to find the measure of angle C, we see that the measure of angle C is 2x plus 6 degrees. So now as I do is I'm going to plug this 16 in for the x, so 2 times 16 plus 6, and that's going to give me 32 plus 6, so that's going to be 38 degrees is the measure of angle C. So there's all the work that I need for this particular problem. Now we just had the ITT theorem, which was P arrow Q, which basically said if the two sides are congruent, then that implies that the angles are congruent, the base angles are congruent. Now what we're going to do is we're going to look at the converse of ITT, the converse of the isosceles triangle theorem. And so what we're going to do here, as you guys are hopefully already well aware of, is we're going to take the P and the Q and we're going to switch them around. So that's exactly what we're going to do here. So here we say if the base angles are congruent, so in other words, if two angles of a triangle are congruent, then the sides opposite those angles are congruent. Okay, so this goes from angles implying sides congruent, and then ITT was sides implying angles congruent. So let's see an example of that. So here we are asked to find the length of segment AB and the length of segment CB. And what we can see here is, this is actually not a great picture, so I apologize. I mean, we can already see that this segment's congruent to this segment, which I was kind of, I guess I should have thought about this one a little bit more. I was wanting to have assumed that segment or angle A, or I'm sorry, angle C and angle B were congruent. Therefore, the opposite sides are congruent by the converse of the isosceles triangle theorem. Nonetheless, we can go ahead and proceed from there. So 2x minus 1 has to equal x plus 7 by the converse of ITT. Now you could just say, well, Mr. Allen, they're marked congruent, but I accidentally left those markings in there. So anyways, moving on. So we can solve this and we're going to get x equals 8. So we got x. Now the question is what's the length of AB? So the length of AB denoted AB with no marking over it. Well, AB is x plus 7. So now we're just going to plug the 8 in for x and we'll get 15. So the length of segment AB is 15. Now I also want to find the length of segment BC. That's this guy down here. So BC, I'll call it CB because that's what I said, is x minus 4. Now we're going to plug 8 into that. Of course, that's going to be 4. So the length of segment AB is 15. The length of segment CB is 4. All right, let's talk about equilateral and equiangular triangles. So this is an equilateral triangle. It has the word or the sub root word equi and also lateral. So this is equilateral, which means equal sides. So all 3 sides are equal. By the way, this is a subset of isosceles triangles because, as you know, isosceles triangles have at least 2 congruent sides, and an equilateral triangle just has all 3 of them, not just 2. And this over here is what we call an equiangular triangle. So this is equiangular, so equal angle. So all the angles are 60. So we've got 2 theorems about equilateral and equiangular triangles, and they are converses of one another. So the first one says that if it's equilateral, then it's equiangular. And the second one says if it's equiangular, then it's equilateral. Oh, we can combine these into one theorem. We could simply say equiangular, or I'm sorry, equilateral, doesn't matter. Equilateral, if I can spell, I think I misspelled equilateral. Yes, that should be an R, sorry. If and only if, sorry guys, I got a little distracted there. Let's try that all over again. Okay, equilateral if and only if equiangular. Let's make sure I spell this correctly. So instead of having 2 theorems, you could just know this. If it's equilateral, then it's equiangular. If it's equiangular, then it's equilateral. All right, so example 3 here says, find the values of x and y. All right, so let's first start with, y, if that's okay. Just because x comes first doesn't mean we need to do that first. First of all, what do we know is true? What do we know is true about all 3 angles of a triangle? Well, we know that they have to add up to 180 degrees. So I'm going to argue that 60 plus y has to equal 180. So 120 plus y has to equal 180. And y will be 60 degrees. Or y is 60, I guess, just 60. Oh, now that's interesting. If all 3 angles are 60, in other words, they're all equal angles, that implies that it has to be equilateral by our previous theorem on the last slide. which means that this segment has to be congruent to this segment, has to be congruent to that segment. And we know that all three segments have to add up to 54. So that means if this is 4x, this also has to be 4x, and this also has to be 4x. So we're going to get 4x plus 4x plus 4x. The three sides have to add up to the total perimeter, which is 54. In other words, 12x is equal to 54. And now we need to divide both sides by 12. You will get x is equal to, and I'm going to get my calculator here. Let's see what we get here when we do 54 divided by 12. And I get 4 1/2, so 4.5. So we have found y, and we have found x. There's one extra theorem here in this chapter or this section that I will mention, and it basically says the following. If a line bisects the vertex of an isosceles triangle, then it also is perpendicular bisector of the base. In other words, what I'm saying is this. If you've got an equilateral triangle like this, and you draw the angle bisector of the vertex angle, remember the vertex angle is this angle up here, we know that this side's congruent to this side, then what it's saying is that this line is perpendicular and it bisects the base. So it's a perpendicular bisector. It's kind of a fancy set of words there. I'm not going to do any examples of this last theorem. So what I would encourage you to do is to summarize in your own words the big ideas from today's lesson on isosceles triangles and equilateral angles, or equilateral triangles. Have a good day.